One Kaz Wilson made a nice comment on my channel after I posted this video on this podcast on PM 2.5, saying maybe I should explain what PM 2.5 is. I did that in other podcasts, but each podcast has to be, independent in that sense. So it's a good point. Thank you, Kaz. I don't know you, but thank you for making the suggestion. So PM 2.5 is part of the pollution. When we talk about pollution, there are all the chemical pollutants like sulfur dioxide, nitrous oxide, you have carbon monoxide and so on. There is a plethora of them. And then there are the particulate matters which are abbreviated as PM, and they have sizes associated with them, like PM10 is particulate matter smaller than 10 microns or micrometers. PM 2.5 is 2.5 micrometers or smaller, and these are deadly dangerous because you can hardly see them unless it's in a large concentration, but you're constantly breathing them, and new research shows the dangers of these small particulates, which obviously get into your lungs and cause all kinds of respiratory diseases. But now new research says they actually can find their way into the bloodstream through the lungs, directly through your nostrils, through the digestive stream, digestive tracts, and so on and so forth. And then they're associated with increased dementia, cognitive disabilities, attention deficit, as well as diabetes, and so on and so forth. So that's PM 2.5. Now I'm going to add this little piece to the other podcast, which actually is in a different shirt because I'm adding this a day later. So ignore that part and just focus on the results that we are reporting on how PM 2.5 has grown across the world and how the exposure to PM 2.5 is unequal in the global south versus north. But actually you can go into the details of a city like Chicago or Philadelphia and find that even within a neighborhood these exposures are very unequal, or at a state level like California, where the power plants are and where PM 2.5 is high, who lives there, etc. Okay, so let's switch to the podcast on the paper on growth of PM 2.5 and unequal exposures. Okay, so this is a new paper that looks at the PM 2.5 distribution over a couple of decades. The real new thing here is that they take the available data, they combine it with the transportation model and other geographical information that's relevant, and then they use what is called deep ensemble machine learning, which is an AI method, to interpolate the data to put together a gridded product for daily exposure to PM 2.5. And as you can imagine, the exposures are not equal. Even within a country like US, for example, the California state, for example, if you take power plants and where they're located and who's exposed to those particulate matter emissions, then obviously poorer neighborhoods are typically chosen to establish those power plants. Just happens, and you can call it racism. There is a lot of literature in the US on how ethnicities and races are part of the exposure inequalities as well. But coming back to this particular paper here, we are going to look at mean annual PM 2.5 micrograms per meter cubed, and the scale goes from less than 5, which is better than the WHO standard for safe levels, to greater than or equal to 75 micrograms per meter cubed, which is orders of magnitude higher than what WHO recommends. These are the global monitor station distributions and mean annual PM 2.5 concentration over 2 decades from 2000 to 2019, and you can see that the coverage is pretty good in the US, but still there are big holes. Canada is much less so, and if you look anywhere else in the world, China has a good distribution of monitoring stations, so does Europe. But remember that these are big dots corresponding to the coverage, plus also the mean annual values, especially if you look at a country like India, which is highly polluted. Then you see that the coverage is not as good as it should be. So the reliability of the extrapolation and interpolation in time and space to produce a gridded map requires some validation. So these are kind of the comparisons between observed and model estimated PM2.5 concentrations over the same period of 2000 to 2019. So you're looking here at observed mean PM2.5 in micrograms per meter cubed, sorry, and you are looking at monthly and then annual means. Obviously, as you go down to daily time scale, the predicted annual mean PM2.5, the correlation is fairly high, the regression is pretty good, R squared of 0.91, RMSE of 7.86 microgram per meter cubed, and here are the data counts. The spread is expected to be larger when you go to very fine resolution in time. As you average over a month, the match gets better between predicted and observed, and for annual mean it gets much better, of course, with R squared of 0.98. It's 0.96 here. Obviously, annual mean values have very little realistic value. For example, a country like India, where the monsoonal system completely reverses the wind circulation, source and sink locations for the PM2.5 tend to be very different as well. So we do need daily exposure counts, and models are reliable to the extent that the spread is large but the correlation is high. Looking now at the annual mean PM2.5 in 2000, 2010 and 2019, and changes in annual mean PM2.5 per decade at 0.1 degree by 0.1 degree spatial resolution. So that's literally at around 10 kilometers, which is incredibly high resolution. The change in annual PM2.5 per decade was calculated by multiplying 10 years with the coefficients of a linear regression model established from 20 annual mean to PM2.5 values for each global grid cell. So kind of a detail on how it's done. Nonetheless, looking at annual PM2.5 concentrations in 2000, you can see in micrograms per meter cubed. If you look at countries like, let's say, India and China, and look at some parts of the US, the values from 2000 to 2010, they are higher, especially in the Himalayan foothills and central Indo-Gangetic plain going into Pakistan, Iran, and so on. China, the northeast corner, is very high concentration going from here. You can see the darker colors have a larger area coverage here. The concentration has increased by 2019 as well. And if you look at change in annual mean to PM2.5 concentrations per decade, that's reduced in some places like the eastern central US, extending all the way from north to south, whereas the western US and northeastern Canada have gotten worse in terms of increases here. The regions of China and India that have gotten worse show up very clearly in the trends in terms of annual mean PM2.5 concentration change per decade. Africa has this pattern of getting better in the sub-Sahel region, but getting worse in North Africa, Sahara, but northwestern Africa here has gotten better. Europe looks much better. It's not always clear whether this is related to economic turndowns and or actual actions taken to move to renewables, reducing emissions, more EVs, better, switching to natural gas as opposed to oil and coal, for example, and so on. So the details of exactly why the trends are downward in some places has to be figured out as well. Looking at the changes in annual mean population weighted PM2.5 concentration and annual population weighted exposed days by region for 2000, 2010 and 2019, the bar chart shows the proportion of population weighted exposed days with PM2.5 concentrations higher than the 2021 WHO air quality guideline, which is at 15 micrograms per meter cube in a year. Data points and connecting lines show the annual mean population weighted PM2.5 concentrations, and error bars show the standard deviation. So you are looking here at various regions: Asia, Central Asia, Southern Asia, Western Asia and Eastern Asia, and you can see the annual population weighted exposed days in terms of percentage from 2000 to 2019. Overall in Asia hasn't changed that much. The slight dip in 2019 compared to 2010 is probably within the uncertainties. Remember, these are interpolated, extrapolated, gridded product produced from a small amount of actual data. Central Asia is lower than overall Asia and may have taken a little dip by 2019. Southern Asia is bad, which includes India, Pakistan, Bangladesh, Nepal, and so on, and it has increased over this period in terms of the mean as well as the standard deviations. Western Asia is lower than even Central Asia, and Eastern Asia, which includes China, is obviously the highest in this region. You can similarly look at Americas with Northern and Latin America and the Caribbean. They are much lower compared to Asia. Good God. Annual population weighted population weighted PM2.5 is given on this axis for all these plots. So again, looking at Europe, took a nice dip in 2019. Northern Europe is lower and remained relatively flat in terms of annual mean population weighted exposed days. Southern Europe, Western Europe, Eastern Europe, and so on. Africa, as we said, Northern Africa increased, but Sub-Sahel remained flat or decreased a little. This is Oceania, Australia, New Zealand, other subregions in Oceania. They have relatively low numbers when it comes to annual population weighted exposed days as well as annual population weighted PM2.5 concentrations. So there we are in terms of global means, which are not that useful when you consider impacts on health and so on. There are very region specific local data that is important for exposure and health outcomes. Nonetheless, for global circulation, impacts on global warming and impacts on precipitation, etc., global means still have some value. In terms of looking at rankings, leading countries for annual mean population weighted PM2.5 concentration and population weighted exposed days in 2000, 2010, and 2019. Values in parentheses are standard deviations for PM2.5 concentration, or they are percent for a proportion of days out of 365. The 2021 WHO Air Quality Guideline limit for daily PM2.5 is at 15 microgram per meter cube. This was the threshold for population weighted exposed days. Income categories are based on the World Bank classification data for the year 2019. When you say unequal exposure, you have to consider all these things: socioeconomic strata, etc. So going back to this one here, you can see annual mean population weighted PM2.5 concentration. Leading countries in 2000, number one was China. In 2010 it was still China, in 2019 it was still China, and the numbers went down a little from 2010 to 2019, but not much. Niger it was bad in 2000, but went down to number 5 by 2010 and up to 4. So if you look at other countries, India was at number 15 here, but it jumped to number 9 by 2010 and number 8 in 2019. So not really systematic improvements in as such. So Egypt, for example, went from 34 to number 10 in 2010 and remained at number 10 in 2019. The numbers went from 30.9 micrograms per meter cube to 36.9 and 37.9 respectively for 2010 and 2011. So none of the places are systematically getting better. Small countries like Mali here went from number 6 to number 12 and doesn't even show up in the top 10 for 2019. Okay. Looking at other places, looking at oops, did I? Okay, I just showed This is the second part of it. Annual population weighted exposed days with PM 2.5. So Niger was number 1 in 2000, went down to number 4 in 2010 and remained at number 4 in 2019. China was at number 5 with 354 exposed days, which is terrible. It went up to number 3 with 353 exposed days. We know that concentration went up. Then it has dropped to number 13, but the drop in number of exposed days is not significant. It's still at 336. If you look at India in 2000, it was at number 7 with 351 exposed days, and it went up to here down to number 8, and then it's at number 7 by 2019 with 351 days, just as it started in 2000. So no improvements as such. Economic growth has come with increased energy production. A lot of it is coming from coal in India and China, which increases PM 2.5 by a lot. Number of vehicles have increased, construction has increased. Monsoon rainfall has trended down, so that tends to increase the non-rainy season dust loading PM 2.5 as well, and so on and so forth. Okay. Monthly mean PM 2.5 in micrograms per meter cubed. If you look at January, February, March, June, and then there are other months here. Obviously, seasonally varying places like India and China are very critical. So if you look at non-monsoon days during October, November, December, January, there is some rain due to northeast monsoon in some corners of India, but otherwise it's winter, it's inversions, and you see high concentrations here in the Himalayan foothills and or much of the Indo-Gangetic Plain, Western Ghats, and so on. Looks like a little bit less in February. March has got much wider region of higher concentrations. April and May, so by June when rain comes, you expect the concentrations to begin to drop, but you can see that that happens, but not as significant as you expect. But the contrast going from the end of the monsoon season into the northeast, so end of the summer monsoon into the northeast monsoon, you can see the ramping up of the concentration in the Himalayan foothills into Nepal. Lots of crop burning, wind changes, inversions, and so on, increasing the monthly mean PM 2.5 concentrations. Okay, so that's a very brief introductions. The new result here really is how they have combined machine learning techniques with transportation models and other information to take the very sparse observed data to produce this gridded global data. Obviously, the data gaps are still large and should increase in terms of just increasing the monitoring stations, and then there is the next part of actually mapping these onto health outcomes and how they have changed over this 2-decade period going from 2000 to 2019. Okay, so I'll leave it here. Actually, I should emphasize one point here that I didn't, so I restarted this podcast. Essentially, if you look at the maps of annual mean concentrations and the next figure, which shows different regions from decade to decade, you can see that pretty much the entire world has, especially the global south countries, developing countries, have concentrations of PM 2.5 way back from 2000 to 2010 to 2019, concentrations above 15 microgram per meter cube, which is the safe standard as defined by the World Health Organization from the health perspective. And many places have gotten worse, as we said, especially India and China, and even parts of western US into Canada, eastern seaboard, and there are a few places like Sahel and Europe which have gotten better. But what matters is not whether they got better, but how much they got better, and whether concentrations really dropped below 15 micrograms per meter cube, the safe level, and that's not the case. And the same thing we saw here in different regions as well. This is annual population weighted exposed days on this side, but annual weighted population weighted PM 2.5, which are, the scale of 0 to 60 here, and you can see that pretty much all regions are way above 15 microgram per meter cube, except maybe the Americas. Actually, even they are above 15, but some of them dropped, like Northern America has dropped on average, and Latin America and the Caribbean has gone up from just being above the unsafe levels to being much higher than unsafe levels. Or higher than safe levels, sorry, and similar story everywhere. So the headlines that have been blaring after this paper is that less than 1% of the Earth has safe levels of PM 2.5. That's basically true, yet the unequal exposure, the vulnerability and risk to health from PM 2.5 depends on what measures the exposed population can take. If you are living in a rich neighborhood and you have a car that has AC, then your exposure is going to be much less, despite the concentrations in the air being above safe levels. So all those things have to be kept in mind. So I just wanted to add that at the end for a couple of seconds, because I didn't emphasize that point enough when I recorded the podcast. Okay.